The sanctions were supposed to freeze China's semiconductor industry in place. That was the theory back in October 2022 when the U.S. Commerce Department dropped export controls on advanced AI chips, lithography systems, and semiconductor tooling. Washington believed something very specific. If China lost access to the highest-end manufacturing ecosystem, the gap would widen permanently. No EUV machines. The massive build-sized lithography systems that use extreme ultraviolet light to carve microscopic pathways onto silicon. No cutting-edge AI accelerators, no path forward. It looked like checkmate. Instead, something strange happened. Chinese firms started replacing foreign suppliers faster than anyone predicted, and one chip in particular changed the mood inside the entire industry. Not because it was the most advanced processor ever built. It wasn't, not even close. The shock came from a completely different direction. Global customers began moving orders away from Taiwan's legendary manufacturing ecosystem toward a Chinese alternative that, according to the original sanctions logic, should not have been commercially viable at all. That shift matters far beyond the world of tech enthusiasts, because chips are no longer just electronics. They are industrial oxygen. Cars, cloud computing, weapon systems, hospitals, shipping ports, banking infrastructure. All of it runs on semiconductors. Today, a disruption in chip supply chains doesn't feel like a software glitch anymore. It feels like inflation, sudden layoffs, export restrictions, delayed factories, governments abruptly discovering they are entirely dependent on companies sitting just 130 kilometers off the coast of mainland China. Which is why a single number started making global supply chain executives incredibly uncomfortable. Most people never heard it. Procurement managers heard it. The people who actually decide where billions of dollars in manufacturing contracts go heard it. 80%. In several mature node categories: power management chips, display drivers, industrial controllers, automotive microcontrollers. Chinese suppliers reportedly began replacing large portions of orders that previously flowed almost automatically toward Taiwan-based manufacturing networks tied to TSMC, the undisputed king of advanced fabrication. Notice that phrase, mature node. It sounds boring. It sounds like yesterday's news. It isn't. For years, the public conversation focused obsessively on 3nm and 5nm chips because they power AI models and flagship smartphones. But mature node chips, the 28nm, 45nm, and 65nm silicon, are the workhorses that actually run the physical world. They operate washing machines, cars, factory robotics, medical equipment, elevators, and missile guidance systems. During the pandemic-era chip shortage, automakers weren't waiting for cutting-edge AI chips. They were shutting down entire assembly lines because they couldn't source relatively old, unglamorous semiconductor components. China noticed that vulnerability before most Western analysts did. Instead of chasing the absolute frontier everywhere at once, Beijing pushed enormous state-backed capital into the parts of the market where scale mattered far more than elegance. Provincial funds, the National Integrated Circuit Industry Investment Fund, usually called the Big Fund, and municipal governments started pouring financing into fabrication plants that most Western investors considered unprofitable or outdated. They didn't build sexy AI chips, they built industrial volume. There is a massive difference. A factory producing millions of mature node chips at a lower cost can quietly reshape global supply chains without ever winning headlines. While American restrictions focused heavily on preventing breakthroughs at the absolute leading edge, China spent years building massive capacity underneath the conversation. This is where the story gets awkward for both sides. The American narrative said China could not replicate critical semiconductor ecosystems without Western tooling dominance. The Chinese narrative implied sanctions barely mattered at all. Neither version survives contact with reality, because what actually happened is far stranger. China didn't leapfrog Taiwan. It changed the battlefield entirely. And the company sitting at the dead center of that shift is not operating the way most people think. In fact, one of the most important advantages it possesses right now isn't breakthroughs in physics or genius engineering. It is a terrifying tolerance for pain. There is a habit in Western tech analysis that keeps producing bad predictions. People assume the most advanced technology automatically wins the market. Sometimes it does, but often it doesn't. Intel had better engineers than many competitors for years and still stumbled because manufacturing discipline broke down. Japan once dominated memory chips, then lost ground despite having world-class technology. Meanwhile, companies selling older semiconductor nodes kept making absurd amounts of money because the world still needed billions of cheap, reliable chips that could survive inside a car engine or a refrigerator for 10 years without failing. That is the exact layer China targeted. Back in 2014, Beijing launched the first phase of the Big Fund with roughly 138 billion yuan. The second phase followed in 2019 at over 200 billion yuan. Most headlines focused on Huawei or high-end AI processors, but a massive portion of that money flowed toward raw fabrication capacity, materials localization, advanced packaging, and industrial chips, the boring parts, which, in large-scale manufacturing, are usually the only parts that matter. If you run an automotive company, you don't need the world's fastest processor to control a windshield wiper or a battery sensor. You need a supplier that can deliver 20 million units on time at retail prices during geopolitical chaos. Reliability becomes strategy, and this is where the trap snaps shut. China's mature node expansion happened at the exact same moment multinational firms became terrified of concentration risk around Taiwan, not because they believed war was imminent tomorrow morning, but because corporations think in probabilities, insurance costs, shipping exposure, and shareholder panic. Even a small risk matters when your entire production line depends on one island. So companies started diversifying, quietly at first. A purchasing manager changes 12% of orders, then 20%. Then a supplier in mainland China undercuts competitors by enough margin that finance departments stop resisting. Gradually, a network effect forms. Once a factory reaches high utilization rates, production costs drop further, which attracts more orders, which funds more expansion. Take the display driver chip market, the silicon that tells every pixel on a screen what to do. Chinese fabs, supported by aggressive subsidies, began capturing contracts that historically belonged to Taiwan. Not because Chinese chips were superior, but because they were available, cheaper, good enough during a period when global buyers feared disruption more than they feared imperfection. Good enough may be the most dangerous phrase in industrial competition. American policymakers thus largely framed the chip war around technological ceilings. China responded by weaponizing industrial floors, but there is another deeply uncomfortable layer here that people avoid discussing openly. Democracies are often bad at sustaining expensive industrial patience. Election cycles reward visible, short-term wins. Semiconductor ecosystems operate on timelines closer to aerospace or nuclear infrastructure. 10 years disappears quickly. China's system has obvious, glaring weaknesses. Wasteful spending, ghost projects, massive corruption scandals, and entire chip startups that absorbed billions before collapsing into accounting disasters. Some facilities barely produced functional silicon wafers. One local government reportedly invested heavily in a semiconductor project before realizing the founders didn't actually possess the technology they claimed to own. But here is the twist most analysts miss. Even failures create infrastructure. Unused factories still train technicians. Failed suppliers still produce technical knowledge. Machinery imported for one collapsed project often reappears somewhere else. Human capital spreads through the system whether investors recover their money or not. That accumulation effect matters far more than quarterly headlines. Washington's assumption seemed to be that denying China access to frontier technology would freeze capability development across the board. Instead, it created an artificial pressure cooker, forcing localization at every layer simultaneously: chemicals, silicon wafers, packaging, deposition tools, and industrial software. Which brings us back to that 80% figure. It wasn't about one miracle chip replacing TSMC technologically. It reflected a growing number of global buyers deciding they could live without perfection. But if you only listen to Chinese state media, you'd think the semiconductor war is basically over, and China has already won. That is completely false. China still depends heavily on foreign technology in critical areas. Advanced electronic design automation software is still dominated by American firms. The highest-end graphics processing architectures are still concentrated inside Silicon Valley. This is not some clean victory march. The original strategic objective behind the sanctions was to preserve a durable technological distance large enough that China could not translate industrial scale into strategic independence. The expectation was that missing one critical layer, EUV lithography especially, would bottleneck the entire ecosystem indefinitely. Instead, the ecosystem adapted sideways. Imagine trying to block a massive river with a concrete barrier, only to realize the water has started spreading through dozens of smaller channels you weren't monitoring closely. Less dramatic, less visible, but still moving. And right now, those channels are converging on a part of the microchip manufacturing process that Western planners completely overlooked. A sector that is about to give China a massive, unexpected lever over the future of artificial intelligence hardware, without ever needing to build a single advanced lithography machine. To understand how that's possible, we have to look at a factory floor that doesn't look like a semiconductor lab at all. That overlooked sector is advanced packaging. For decades, packaging was treated as the janitorial work of the semiconductor world. In the traditional hierarchy of tech prestige, the glory went to the front-end fabrication. The physicists and engineers using multi-million-dollar lithography machines to print billions of microscopic transistors onto a slice of silicon. Once that ultra-precise printing was done, the wafer was chopped up into individual dies and sent to packaging facilities, usually located in regions with low labor costs. There, technicians essentially glued the piece of silicon onto a plastic base, wired up the connections, and sealed it in protective epoxy. It was low margin, low tech, and completely ignored by Wall Street. But a fundamental law of physics has flipped that entire dynamic on its head. For over 50 years, the tech industry worshipped Moore's law. The observation that the number of transistors on a microchip doubles roughly every 2 years, making electronics twice as fast and twice as cheap. To keep that rhythm going, engineers had to make transistors smaller and smaller. We went from measuring features in micrometers to nanometers, entering a realm so infinitesimally small that a single transistor is now narrower than a strand of human DNA. But we have finally hit a physical wall. When you shrink a transistor down to just a few nanometers, the laws of classical physics start to break down and quantum mechanics take over. Electrons begin to misbehave. They leak through insulation layers like water through cheesecloth, causing chips to overheat, waste power, and glitch. Worse, building these atomic-scale frontiers has become economically ruinous. A single modern fabrication plant now costs upwards of $20 billion. Printing a giant monolithic chip, where every single component of a processor is crammed onto one massive piece of silicon, means that if even a single microscopic speck of dust lands on the wafer during production, the entire chip is ruined. As chips get bigger to handle complex AI workloads, the yield, the percentage of functional chips per wafer, plummets. This is where the industry's secret workaround comes in, chiplets, instead of trying to force a massive, perfect, all-in-one superchip through an incredibly expensive manufacturing line. Engineers realized they could break the chip apart into smaller, specialized modules called chiplets. Think of it like building with Legos instead of carving a statue out of a single block of marble. You manufacture a small memory module, a separate processing module, and a specialized power regulator on whatever node makes the most economic sense. You can build the core processor on a highly advanced, expensive 3-nanometer line, but leave the communication and power components on a cheap, reliable 28-nanometer line. But that creates a massive new engineering nightmare. How do you get these separate pieces of silicon to talk to each other fast enough that they act like a single unified brain? If the data has to travel through old-school wires and plastic packaging, the delay, the latency, kills the performance. The speed bottleneck is no longer how fast a transistor can flip inside the chip. It's how fast data can move between the pieces. This is the exact mechanism of advanced packaging. It is no longer about putting a chip in a plastic box. It is about using microscopic silicon bridges, high-density interposers, and vertical copper pillars to stack and fuse separate chiplets together with microscopic precision. The packaging becomes the chip. To visualize how profound this shift is, imagine a bustling high-density metropolis. The traditional way to make a city more productive was to make every single office building taller and more packed with workers, that is, shrinking transistors. But eventually, the buildings are so dense that the local electrical grid overloads and workers spend hours waiting for elevators. Advanced packaging changes the geometry entirely. Instead of just building taller skyscrapers, you build lightning-fast, multi-lane subterranean tunnels and hyper-efficient sky bridges that connect separate, specialized neighborhoods in 3 dimensions. The city gets faster not because individual desks are closer together, but because the transit system between buildings operates at the speed of light. And this is where Washington's sanctions logic ran into a structural blind spot. The export controls dropped in October 2022 were heavily designed around the front line too. Else, specifically, preventing China from acquiring extreme ultraviolet or EUV lithography systems. The assumption was simple. If you can't print individual skyscrapers at the atomic scale, you can't compete in the modern economy. But advanced packaging allows an engineer to cheat the system by taking multiple, easily manufactured mature node chips, say, two 7-nanometer or 14-nanometer dies that China can produce domestically, and bridging them together using advanced packaging techniques. You can achieve a level of computing performance and power efficiency that rivals a single, monolithic cutting-edge chip. You don't leapfrog the lithography bottleneck, you bypass it sideways. China realized early on that while the front-end fabrication frontier was heavily guarded by a Western monopoly, the back-end advanced packaging ecosystem was highly localized within Asia and highly vulnerable to an aggressive capture strategy. The mechanism of this capture wasn't just throwing money at startups. It was a calculated play for industrial gravity. Chinese packaging giants, backed by state funds, began aggressively expanding facilities capable of executing what the industry calls 2.5D and 3D wafer-level packaging. They focused heavily on advanced interconnect technologies, developing proprietary ways to etch high-density micro-bumps onto silicon carriers so that separate chips could be fused together with gaps measured in microns, while Western analysts were king at the front gate, monitoring whether ASML was shipping its prized lithography machines to Shanghai. China was quietly buying up the packaging infrastructure at the back door. They realized that if you control the packaging ecosystem, you control the final assembly point of modern computing. This matters intensely for the current explosion in artificial intelligence hardware. An AI accelerator like NVIDIA's industry-dominating processors is not just a fast graphics chip. It is an intricate system of a central processing die surrounded by stacks of high-bandwidth memory or HBM. These components must transfer massive oceans of data back and forth every single millisecond to train large language models. They cannot function without an advanced packaging platform to tie them together. By building overwhelming domestic capacity in these advanced packaging methodologies, China didn't just create a workaround for its own domestic AI ambitions. It began creating an alternative gravity well for global supply chains. If a multinational firm wants to assemble a complex multi-chip module efficiently and at scale, the physical infrastructure to bind those pieces of silicon together is increasingly concentrated in facilities operating under Beijing's regulatory orbit. The irony is acute. Washington focused its energy on drawing a hard line in the sand around the smallest nanometer numbers. But by turning advanced packaging into the primary vector of performance growth, the semiconductor industry itself shifted the goalposts. The battlefield moved from the printing press to the assembly matrix, and yet this sideways pivot introduces a massive, underlying paradox that neither Washington nor Beijing openly wants to acknowledge. Because while stacking mature chips can unlock surprising amounts of raw performance, it extracts a hidden, punishing tax that cannot be subsidized away by state funds. A tax that changes the nature of geopolitical leverage entirely. To see where that hidden friction is starting to fracture the industry, we have to look at the one resource that no amount of advanced packaging can optimize. That inescapable resource is electrical power. When you take multiple mature chips and stack them together using advanced packaging to mimic a single cutting-edge processor, you solve the manufacturing bottleneck, but you trigger a vicious thermodynamic tax. Stacking chips vertically or bridging them horizontally creates a dense grid of interconnected circuits that requires massive amounts of voltage to push data across the gaps. Worse, because these chips are physically larger and built on older, less power-efficient manufacturing architectures, they generate immense residual heat. This creates a fundamental structural paradox. If an engineer combines three 14-nanometer chips to match the raw computing muscle of one 3-nanometer chip, the resulting multi-chip module will often consume 3 to 4 times the electricity and run hot enough to warp its own packaging substrate without complex liquid cooling systems. This means that while China's sideways strategy works brilliantly for industrial volume, military hardware, and localized computing infrastructure, it faces a steep efficiency wall when applied to massive hyperscale AI data centers. In the global tech ecosystem, power consumption is no longer an environmental afterthought. It is a rigid limit on how large a neural network can grow. But this thermodynamic reality reveals the deeper, long-term strategic game hiding beneath the surface, a pattern that echoes previous industrial shifts in global history. For the past 30 years, the global semiconductor industry operated on a highly centralized, hyper-efficient model. Design happened in Silicon Valley, advanced lithography machines were built in the Netherlands, precision chemicals were formulated in Japan, and the actual fabrication was concentrated on a handful of highly specialized science fiction-like campuses in Taiwan. This deep division of labor created incredible efficiency, driving down the cost of electronics for consumers worldwide. But it also created a brittle system where a single geological or geopolitical event in a 130-kilometer-wide strait could instantly paralyze global industrial output by forcing decoupling from export controls. Washington inadvertently triggered the end of this unified, hyper-optimized era. The strategic implication is not that China will suddenly invent a machine that eclipses Western physics, but that the global semiconductor market is fracturing into distinct, parallel layers that no longer share the same rules, costs, or standard operating procedures. We are moving away from an ecosystem optimized purely for technological elegance and entering a period defined by raw, industrial gravity. To understand how this plays out, you have to look at the historical precedent of other foundational industries, like steel production or shipbuilding. In the mid-20th century, Western nations possessed the most sophisticated metallurgy and advanced naval engineering techniques on Earth. But over decades, nations like Japan, South Korea, and eventually China focused aggressively on building overwhelming, subsidized industrial capacity at the lower commodity end of the market. Western analysts at the time dismissed this as low-margin, unglamorous work. But once a nation controls the physical volume, the supply chains for raw materials, the specialized machine tooling, and the baseline engineering talent naturally migrate toward that volume. Eventually, the high-end niches become isolated islands, structurally dependent on the massive industrial base beneath them. This is precisely what is happening inside the microchip ecosystem. By capturing the mature node market and anchoring the advanced packaging networks domestically, China is building a deep, resilient foundation of Tier 2 and Tier 3 suppliers. These are the companies making the ultra-pure silicon wafers, the specialized photoresists, the precision wire bonders, and the automated testing equipment. Most people will never learn the names of these companies. They do not have charismatic CEOs giving keynotes in Silicon Valley. But they are achieving something far more durable than headlines: high capacity utilization. In semiconductor economics, a factory that runs 24 hours a day at 95% capacity is a financial engine that generates predictable compounding returns. It allows engineers to iterate continuously, gradually optimizing yields, lowering defects, and quietly moving up the technology ladder one unglamorous step at a time. Meanwhile, Western companies trying to build rival mature node facilities without equivalent domestic market volume or heavy permanent government subsidies find themselves trapped in an uphill battle against brutal cost structures. This creates a massive, long-term dilemma for Western policymakers. If the global economy continues to rely on Chinese for the thousands of ordinary everyday chips that power automobiles, medical devices, and electrical grids, the strategic leverage shifts subtly but permanently. A government does not need to possess the absolute fastest AI accelerator on Earth to project immense economic power. It simply needs to control the components that prevent an automaker in Detroit or a medical equipment manufacturer in Munich from shipping their products. The battlefield has shifted from a race to see who can reach the highest technological ceiling to a war of attrition over who controls the industrial floor. And as global procurement managers quietly adjust their long-term contracts to manage geopolitical risk, they are discovering that the parallel ecosystem China built underneath the sanctions regime is no longer a temporary workaround or a cheap imitation. It has become an independent infrastructure with its own momentum, its own economic rationale, and its own unique set of hidden trapdoors, which leads to the final, most explosive contradiction of this entire technological conflict. Because as both superpowers pour hundreds of billions of dollars into fortifying their respective sides of the Silicon Curtain, quiet calculation has begun inside the secret boardrooms of the world's most valuable tech giants. A calculation that proves the original architects of the chip war may have completely miscalculated where the ultimate point of leverage actually lies, not to see why the entire multi-billion-dollar blockade is about to face its ultimate test. We have to look at a single, confidential spreadsheet that was recently circulated among the largest electronics buyers on Earth. The calculations contained within that confidential spreadsheet point to a reality that is as undeniable as it is uncomfortable for Western policymakers. The pricing floor has officially dropped in the mature 28-nanometer process node, the sweet spot for the chips that manage everything from electric vehicle powertrains to smart factory equipment. Chinese foundries have recently slashed wafer prices by a staggering 40%, dropping the cost per wafer from $2,500 down to $1,500. For a procurement manager balancing billions of dollars in manufacturing costs, a 40% discount is not a miner's incentive. It is an economic gravity well. It forces a brutal choice. Either you pay a massive premium to source your ordinary, daily-use silicon from politically aligned but more expensive foundries in Europe or North America, or you quietly sign the contract with the subsidized Chinese supplier and absorb the geopolitical risk. And as the data shows, the market is already choosing. Projections indicate that within the next 2 years, China's share of global mature node fabrication capacity will climb to an unprecedented 42%. Brands at this is the point where we have to return to the original theory behind the October 2022 sanctions. The strategic goal was to freeze China's capability in place by withholding the crown jewels of Western engineering, the extreme ultraviolet lithography systems. The underlying assumption was that technology is a strict pyramid. If you cut off the apex, the layers beneath it will eventually starve. But what actually happened is that the pyramid turned out to be an ecosystem. By sealing the frontier, the export controls did not starve the base. They transformed it into an insulated fortress. Denied the ability to import Western technology freely, Chinese tech giants and state funds stopped viewing domestic substitution as a luxury or a cost-saving measure. It became a survival directive. Today, that drive for self-reliance has moved far beyond raw fabrication. It has penetrated deep into the foundational elements of the industry that most people never see: the raw materials. By the end of this year, China is targeting over 70% domestic sourcing for the raw silicon wafers used by its chipmakers. 6 years ago, its global market share in that critical substrate sat at a negligible 3%. Today, it is rapidly closing in on a third of the entire global supply. GII researchers show this is the ultimate blind spot of the technological blockade. You can restrict the access to the most sophisticated machine on Earth, but you cannot restrict the mathematics of scale. When a single country builds overwhelming, unmatched capacity in the unglamorous, high-volume layers of an industry, it changes the economics for everyone. Western foundries that rely on commercial margins to survive are finding it increasingly difficult to compete against an ecosystem where profit is secondary to national infrastructure building. As Western firms pull back from these low-margin legacy nodes to focus on high-margin frontier processors, they inadvertently cede control of the industrial bedrock. So, where does this leave the future of the global tech landscape? The traditional image of a single, hyper-connected, globalized supply chain, where components cross oceans 7 times before arriving in a smartphone, is dead. In its place, we are witnessing the birth of a fractured, two-tier semiconductor reality. At the frontier, a small, highly elite club led by Taiwan, the United States, and South Korea will continue to push the boundaries of physics, chasing smaller nanometer numbers and printing the hyper-advanced processors that power next-generation generative AI models. It will be an incredibly sophisticated, highly expensive ecosystem operating behind strict regulatory walls. But beneath that elite frontier, China is successfully constructing an enormous, self-sustaining industrial floor. It is an ecosystem built on mature nodes, advanced packaging workarounds, and guaranteed domestic consumption. It is messy, it involves tremendous capital waste, and it is thermodynamically inefficient, but it produces volume. Millions upon millions of cheap, reliable, good enough chips that keep the modern world turning. The profound irony is that by trying to isolate China from the future of technology, the sanctions may have guaranteed its dominance over the present. The West built a wall to protect the absolute peak of the mountain, only to realize that China was quietly buying up the valley below. And in a modern economy, a skyscraper cannot stand without the ground beneath it. It is easy to watch the headlines and get caught up in the drama of tech prestige. The newest AI benchmark, the smallest transistor size, the multi-billion-dollar factory announcements. But the real shifts in global power rarely happen under the spotlight of a press conference. They happen quietly inside boring spreadsheets, through unglamorous components, and by the relentless grinding force of industrial scale, because at the end of the day, politicians can write whatever restrictions they want. But markets have a stubborn habit of voting for the factory that actually delivers the hardware.